All right, go for it, Maria.
All right, so the important information that I need with this problem.
Hey, Maria's teaching.
The distance between the two plates and their electric, basically the electric field that each of those create. So here's the little electron, and you want to find if it's released from the upper plate, so it goes down because it's an electron going to the positive side, you need the speed. So basically, the information that we have is E. We also have Q, which is on the equation sheet, and we have the mass of the electron. So with that, because we know that E is equal to Q, no, I'm sorry, F over Q is equal to E, we can take E, which is 1 times 10 to the 4th, and multiply by Q, which you have, which is 1.6 times 10 to the negative 19. So if you plug that in, you'd get the force of the electric field, which would end up being 1.6 times 10 to the negative 15. And then because we know that force is equal to ma, we want to find the acceleration of the electron as it's moving to the positive side. So again, you plug that in with the mass of the electron and acceleration, you end up getting a really big number. So it's 1.76 times 10 to the positive 15.
If you have questions while she's working,
you can
raise your hand, pause her, slow her down, because this is when we're going through this question. So feel free. They're going to do the same thing to you. So.
No questions?
No
questions. And so now that we have the acceleration, we have the distance, we can use kinematics. So you can create your table. The initial position is 0, the final position is 1 centimeter. V, that's what we're trying to find. And then it also says is released from rest. So the initial will also be 0. We now have A, and time we don't have. So then you can use.
What was the distance?
0.1 meters.
Oh, 0.1 meters.
Yeah.
1.01.
Huh?
0.01. 1 centimeter.
Yeah, 1 centimeter.
And then you can use V squared equals V naught squared plus, plus 2A, because we don't have time, so we don't want to use the one with time. And then you plug all of those in to get, so this cancels out as 0, this is 0.1, and this is 2 times that really big number. And then you square root it, and you get V equals 5.9 times 10 to the 6th. So that's the first part. And then the second part, you're still going to use kinematics, but you're going to use V equals V naught plus A T to find time. So it's just a kinematics problem, and time ends up being 3.4 times 10 to the negative 6. All good?
Yeah.
All right. That's it.
Questions?
No.
Should I use?
Great job. Can't you erase it?
Yeah. Yes, you can erase it.
I guess you should ask them. You should ask them. They're the ones who write down the work.
I mean, it's all video, so it's always good for that.
You do have a video. All right. Next up.
Okay, example number 4.
So for the first part of the question, we have to find the electric field strength. So we know the equation for the electric field strength is kq over r squared. So we just use the equation and plug the values in. And then once we plug the values in, for k, we know that the k will be 9 times 10 to the 9th, which is on our equation sheet. Q will be 1.6 times 10 to the negative 19th, which is the charge of a proton or an electron. And the radius is given, which is 5.29 times 10 to the negative 11th. So we square that. And once we do that, we know that we need two significant figures. So solving this, we get 5 times 10 to the 11 newtons. And then for B, we get, to solve for the force. For the force, we know that the equation is k q1 q2 over r squared. Again, we just plug the values in. For k, we get 9 times 10 to the 9. For both charges, we get 1.6 times 10 to the negative 19. And the radius, which is the distance, is also given. So solving that, given for two significant figures, we get the force is equal to 8.1 times 8.2 times 10 to the negative 8th newtons. And then for C, we need to find the speed of an electron. So we can recognize that the electron is moving in a circular motion, which means that it must have a centripetal force, which is keeping it in its orbit. So we know that the Fc, which is centripetal force, is equal to mv squared over r. We know that the mass will be 9.11 times 10 to the negative 31st, which is the mass of an electron. And we're solving for the velocity. And we know that the radius is also 5.29 times 10 to the negative 11. So putting that into your equation with the solver function, we get that the velocity is equal to 2.2 times 10 to the 6th meters per second. Yeah.
Why do we use the same charges as
Because they both have the same charge. It's just a proton is positive and an electron is negative. Yeah, remember how in chemistry you learned that the number of protons, if that was balanced with the number of electrons, you had an electrically neutral atom. Like a hydrogen has one proton, one electron. The reason why is because if they both have the same charge, then the atom itself is neutral. If you have a helium has two electrons, two protons, two neutrons. The neutrons don't have any charge, so the two protons have to have the same charge as the two electrons. Otherwise, every single atom would have a charge, and that would cause interactions with other atoms. So in order for them to be neutral, we believe that that must be the case where they have the same charge. Yeah, good question. And so in your formula packet, they give you the elementary charge, which is 1.6 times 10 to the negative 19, and you recognize that that's positive for a proton, and that's negative for an electron. But otherwise, the value is the same, the magnitude is the same. All right, are we good with that one? Mm-hmm. Circular motion. Remember the good old days? Good old days are back. You just get to do more with it. All right, go for it, action. Sorry, I'll give you your next one. There we go. It was out of focus. I need to. Number 5.
So here we're looking at two positive charges, which are 16 microcoulombs and then 4 microcoulombs, separated by a vacuum, a distance of 3, and we're looking at the net electric field, which is 0. So both the electric fields have to equal each other. So E1, E2, and so to solve for the placement here. And you do that by equaling both the charges. So you solve. constant times the charge, which is 16 times 12.
So that's
And
the
solve
electric field due to charge 1.
Yeah. Now it gives you 4. And solving for E2.
Why can't you use the D? The 3 meters for the D. You don't know the D.
Yeah. Oh, what do you mean? What?
Oh, okay.
That's what you're trying to find,
Yeah.
is where exactly.
Okay.
They've defined D for us, so he was exactly right to go ahead and use that D.
Okay.
D is the distance from 1 to that point, wherever it is.
Okay.
And so he's using the variables that they gave, which is what you should do.
And then you like do the same thing with these two numbers. And for the distance, it's 3 minus d because it's looking at this part. So it's 3 minus d. Then that gives you 36,000.
And again, he did exactly the right thing by defining that distance in terms of the variable that he already had. If you used a different variable there, you wouldn't be able to solve it, because then you'd have 2 variables. It'd be another equation if you were going to try to do that.
And because they both have to equal each other, you set them equal and you put it in the solver. And when you put that in the solver, you get D.
2?
2. Yeah.
2 what?
Oh, 2.
Because you've done everything in meters and seconds and newtons and coulombs, so therefore it should be SI.
2 meters.
Good.
So this would be 1. Cool. Any questions?
Okay, so this one's a little complicated, so pay
Just a little.
attention, you guys.
Just a little.
Okay, so we are given two 5-gram point charges on 1 meter long threads that repel each other after being charged to 100 nanocoulombs, as shown here, and they're asking us what this angle is. So the way that I started it was I drew a free body diagram for one of these charges. And so what we would have here is tension. This way, we have Fg, because it has a mass. And then we have the force from the repelling force from the other charge that is here, that is the Fe. And so what I did was I did the second law, equals ma, and I wrote an equation for both the vertical and the horizontal. So for horizontal, you would have tension times the sine of this angle right here, which I called 90 minus theta, because 180 degrees in a triangle, this one's 90, these two have to add up to 90, so 90 minus theta. Minus
What would be an alternative option?
cosine theta.
You could just use theta.
But I was trying to think of it in terms of this specific place.
Which is fine, and that's fine. What she's done is fine. So I just wanted you to be able to where you don't have to do the 90 minus theta. You could just use the theta.
Can you repeat what you said you knew it's 90 degrees?
Yeah, because triangle has 180 and this is 90. So this plus this must be 90,
Yeah.
right? So 90 minus theta. And that should equal 0 because it's in equilibrium. It's not moving. It's not accelerating. And so from this, I rewrote this equation for t. And so that t was equal to Fg divide, well, I mean, first of all, I guess you could move this to the other side, and and then you can write it as T equals Fg over sine of this. And the reason I did that is because then I wrote out the horizontal equation, which would be the electric force to the left plus tension, but this time the other component. So now I can plug in this for tension here, so that I only have one unknown. Well, aside from this, one unknown variable. So that's exactly what I did. So I did, and I even rewrote it so that it'd be Fe equals to Fg sine cosine then
give them a second and see their speed writing. You guys okay with
Yeah.
yeah, okay.
so far?
Then, so I knew that the electric force had to be equal to this, and there's an equation for that. Fe equals K Q1 Q2 over R squared. We know what K is from our calculus, and we are given the charges. So the only thing that we wouldn't know is R. And the way that I got R was I just used this value that they gave us, 1 meter. 1 meter times the cosine of this angle, 90 minus theta, is equal to this little distance. This is half the radius from these 2 points. So multiplying that by 2, that is our radius. Does that make sense? And then, so I plugged in the values. I plugged in this for R. And then I got an equation that was like 0.049 cosine 90 minus theta over sine 90 minus theta is equal to, so this is Fe, is equal to what I had, what I had, actually no, this is Fg, I think. This is this one. And then I plugged in this for Fe. Yeah? Yeah, okay. So I plugged in the values for this, and then I had an equation, and then I took this and I set it equal to this.
Just the first part of that?
Yeah, so all of this is equal to this with the numbers. And so that would look like this.
So the 0.049 is your FG.
Yeah.
That's when you put the mass in
That's
9.8 in.
That's this.
So that's the FG. And then you see the sine of 90
Sine
minus
and
theta is still on the bottom, and the cosine of
Cosine
90
is-
minus theta
yeah.
is still on the top. So that's just the original equation she had was the Fe equals Fg over sine theta cosine theta. And that's equal to the other equation she just came up for the electric force, which is the K1 Q2 over R squared.
And so if you plug that into a solver, you get that theta is equal to 4.42 degrees.
Yeah, you have to solve that. You just put it in a calculator.
And that's it.
What does it say? It says G times 10 to the negative fifth on the right side. The full right. Yeah.
That's 9.
And that's just the.
That's
the
that's
K2
all of
over
this.
Q2 over
Yeah,
R.
it simplifies to 9 times 10 to the negative. Because the charges were hundredths, so
Right? Give her a hand.
that's complicated.
So, forces, right? She did the horizontal forces, she did the vertical forces, and then she did the electric force by doing the KQ1, Q2 over R squared. Put all that together, put it in the calculator, solve it. Okay. All right. Nice job, guys.
That was pretty good.
That was pretty crazy. When we come in next